let me start recording here also. Okay, so chapter 8 is, as you can see, right, we only have 7 tutorials corresponding to the 7 chapters of our course. Chapter 8 is mostly just like some cool stuff about quantum mechanics and give you a flavor or a preview of how other weird quantum phenomena that we have not discussed in the rest of the syllabus. So one of the main thing is that we will discuss in chapter 8 is the quantum entanglement. So that one is not in the exam, but since quantum every time quantum mechanics is being mentioned somewhere, especially nowadays, is in the context of entanglement, right, and quantum communications and things like that. So we will try to explore this and have a bit of an understanding on that, because when people say quantum entanglement, there's a lot of misconception related to it. So we have that to look forward to. Maybe we do it in the final week of the course, right? But then, yeah, we have 2 more chapters. So 2 more sections in this chapter, then chapter 7 and then chapter 8. Okay, so this one is like kind of what we finished talking about halfway in the previous class. We were revisiting the Stern-Gerlach experiment, right? Now that we understand what does spin mean, it depends on the particle, right? So spin half particles have 2 spins. Spin 1 particles have 3 states. Spin half have 2 states. And when we are talking about a spin half particle, usually you can measure a spin half particle typically originally was done by the Stern-Gerlach experiment. So now we understand, right? Our angular momentum operator, it is h bar over 2 Pauli operator Z. Okay, so last time we were using this, but now we know is this, right? So this is the measurement operator. Everything fine? Yeah. Am I recording? Yes. Check one more time. Yes. So this is the measurement operator for the Z component of the spin angular momentum, right? And so here I'm just gonna remind you a few things, just a bit of a recap, because we kind of stopped talking about it halfway, right? So it's good to to recap a bit. For spin half, we have the eigenstates, right? So eigenstates are, we got the half, minus half, and then half, and then positive half. So now we actually realize that this is the same as the spin down that we did at the beginning, and this is the same as the spin up that we did in the beginning. So the picture that we had in the previous class that I tried to draw last time is, this is telling us the Z component of the angular momentum, and the eigenstate of this is also the eigenstate of the L square momentum operator. So if we plot the angular momentum graph, right, so this is spin down means it has the length of the angular momentum vector has a certain length. So remember, this one is important thing to distinguish also. I'm plotting the angular momentum graph, right? I'm not drawing the physical picture of that particle itself. The particle doesn't literally look like this. I'm drawing the angular momentum vector, which is having a length of 3 over 4 h bar. H bar square, we calculated this last time. And the Z component is negative h bar over 2, right? So this is the Z component, and then the X and Y components are not fixed, so it could be any, so yeah, we just draw one choice. And then for this case, this is still an eigenstate of L square. So this is why eigenstate of L square are the same for these multiple ones. So same eigenstate means I draw the vector of the same length, but this time the Z component is positive h bar over 2, right? So this negative h bar over 2. So over here I draw a positive h bar over 2. So my vector is like this, and then my xy could be is not fixed. So I could have drawn any direction, but I just draw this choice. Okay. So now that we know the what do these states mean. And then when we do the Stern-Gerlach experiment, we pass it through the inhomogeneous magnet. It's split into two beams. So those are the measurement outcomes. Right? So measurement outcomes are the eigenvalues. Okay, so this is how, yeah, the eigenvalue thing is, if you're still feeling it a bit abstract, this is how it works. So hopefully we can kind of see this a bit better now. Connecting the abstract mathematical concept of an eigenvalue to an experiment, right? So again, as a reminder, this is a spin down state, and then this is a spin down state, and then this is the eigenvalue, right? So and then the outcome for the other state is positive half. So you get a positive h bar over 2, and then half, right? So this is the spin up eigenstate. So what we are doing is in the Stern-Gerlach measurement, right? So we have a beam, and then we got the now I can write this as sz, right? So sz, because last time we only write sigma z because we didn't really have the full language to talk about our angular momentum concept yet. But now we know. So now we know this, right? And now it's split into the two beams. So the spin up comes here, and then the spin down comes here. So so the beam that comes here is having the eigenvalue h bar over 2, and then the beam that comes down here has the eigenvalue of negative h bar over 2. So this represents this situation, and this represents this situation. Okay, so now if I know this positive in the up direction, so now I know that this is my state and this is my other state. Okay. Yeah, so and then what else do we write? Yeah, so let us write this in into a more familiar form. Last time that we did was in using the matrix notation, remember? So last time when we did was we did it like this, right? So we just if we just taking out the h bar over 2 part, the factor, we have the Pauli matrices, right? So that your sigma z is acting on spin up is positive 1 eigenvalue spin down, because you took out the h bar over 2 part of both sides of the equation already. And then sigma down is the one with the negative eigenvalue of the sigma down, right? And then sometimes you write the spin up as the so in matrix form, right? You got 1 0, and then your spin down is 0 1. So this is the basis. So if I'm writing this matrix form, right, even in linear algebra, when you choose a set of basis vector like this, right, and then you say that this is an eigenstate of some operator, that means I'm using eigenstates of sigma z as the basis vectors. Okay, so you in this form, then my sigma z was what we showed last time is 0 0 minus 1. Okay, so this one is a brief recap of what we were actually doing. Right now that we really understand when we do the Stern-Gerlach experiment, what is actually happening here is we are measuring the if I align the magnet in the z direction, then we are measuring the component of the particle spin in the z direction, right? The spin component in the z direction only. Okay, so we spent so much time talking about the z direction, especially back in chapter 2. We really seldom talk about the other two directions. So let us finish. Let us catch up with the other two operators, right? So to complete the story, let's talk about the other two. Okay, so let's find the eigenstates and eigenvalues of sigma z, sigma y. Some of them kind of like secretly was a tutorial question already, right? So back when we saw tutorial question, some of them they look so we are just like asking for eigenstate, eigenvalue for some operator which are given. But now we kind of like, now we see the full picture. So now we do it again. So we try to find the eigenvalues. Right, so let's figure out what are the eigenvalues of these two. So let's start with sigma x, right? So remember what was sigma x? The x and y component is the diagonal parts are 0. The other off diagonal is either 1 or I, right? But sigma z is the sigmas are Hermitian operators. So if it's 1, then both must be the same one, so that it is when you do the dagger, it is the same thing. Okay, so that's how at least how I try to remember the operators. What are the eigenvalues? Okay, so eigenvalues, well, we are supposed to solve some equation, right, that obey this. So there's gonna be some state that I act on it, I come back to the same state with a multiple, right? So what's the eigenvalue? So the way to solve the eigenvalue, we do our usual thing. We do this lambda minus I, right? So this is actually finding the determinant of negative lambda 1 1 negative lambda equals to 0. Am I right? And then the formula for determinant is lambda square minus 1 is equal to 0. So I got two eigenvalues, right? Eigenvalue plus 1 or eigenvalue minus 1. So if this is plus 1, what is the eigenstate? So let us plug this in. That means I want to find the state such that it gives me plus 1 of this vector, and my sigma x is 0 1 1 0. I don't know what is this. This is what I want to find out, and it should be able to come back to positive AB again. So this is 0B, this is A, this is AB. So that gives me A equals to B, right? So so A equals to B. So that means for this eigenvalue, right, for this eigenstate, the state, so let's just call this I'm using the plus lambda eigenvalue. So the plus eigenstate is something where the A is equals to B, so both are the same. So if I want to normalize it, normalize it, well, it is a vector where these two components are the same. So to make sure the length is 1, 1 over square root 2. Okay, yeah, so this is 1 over square root 2. And so this is an eigenstate that is positive for the sigma x operator. So I shall just use this symbol up. But the up, to separate this from the up in the z direction, I say that this is up x. Okay, so up x is given by 1 over square root 2, right? 1 1. And then what we recognize is that, well, 1 1 is actually 1 0 plus 0 1. Okay, and this this was the eigenstates of the sigma z operator. So therefore what we conclude is that this one is 1 over root 2 up and then down for the z operator. So I should write z now here, but this was our original eigenstates of the sigma z, right? So these are the eigenstates of sigma z, and as we mentioned just now, we are currently using eigenstates of the sigma z as the basis. This is our basis. Okay, so I got the eigenstate sigma. The eigenstate of sigma z can be expressed in terms of our standard notation of bra-ket for eigenstates of sigma z as this linear combination. Okay, so we can do the same thing. We got two. They're supposed to have two eigenstates, so we need to find the second one as well. What about lambda minus 1, right? So I want to solve the equation. So this is some unknown. It will give me some state again with the negative eigenvalue. So 0 1 1 0, acting on some unknown AB, it gives me negative AB. So this is BA is equals to negative A, negative B, right? So both components just tell me that B is equals to negative A. So now I have found the eigenstates of this. The eigenstates of this is the negative eigenstate of the sigma x. So I shall call this down x, right? So according to this, if this is A, then the B is the negative A, right? And then if I normalize it, so normalize, I'll just say A is 1 over square root 2, then this is 1 minus 1. Okay, so I have concluded that the down X eigenstate is actually 1 over root 2, and then this is 1 minus 1, but I can still express this in terms of our sigma z eigenbasis. This is 1, 0, this is minus 0, 1, right? So my down X eigenstate is 1 over root 2, okay, and this is up in the z direction, and then minus down in the z direction. Okay, so does that make sense? Right? So these are the eigenstates of sigma x, and then these are the eigenstates of sigma z. So now we have found the eigenstates of sigma x operator. One last thing I like to do is to get the ket bra expression of sigma x. Okay, so this one is what we mean by the spectral decomposition, because once we found the eigenstates and eigenvalues, we can do the spectral decomposition. We did this once last time for sigma z in the previous class, but do you remember what do we mean by spectral decomposition? Right? An operator can be expressed as in terms of the eigenvalues and eigenstates. Right, so if you remember, the operator is lambda. If I can find the eigenstates, then I got expressing it like this, right? But for here, I got two eigenstates with these two eigenvalues. So the first eigenstate was up x, right? And then the eigenvalue is just plus 1 here, so it's just a positive number. And then the other one is negative, right? So the eigenvalue is negative down x. The eigenvalue is just negative 1. Okay, so what does this mean? This means is the ket times the bra of this, and then this is also the ket times the bra of this. So we can write this out explicitly. This is 1 over root 2. Okay, so let me put back the ket here, so it is down, and then the bra is like this, and then the second term you do the same thing but for the other eigenstate. So the eigenstate is ket minus up down ket, and then 1 over root 2, up bra, up minus down. Okay, and then you just need to expand this brackets and then simplify. So what we have here is it is half over here, right? Then if I expand, I get up, and then up down, and then down up, and then down, and then the second term minus half, right? So minus half up, down, and then minus down up, and then plus down. Okay, so notice that it's a long expression, but there's going to be some cancellation. See, this is subtracting this, so this term gone. Down is subtracting this, so this term gone, and then this will become plus. So the half and half will add up. It will end up with sigma x is just up, down, up. Okay, so we got the expression for sigma x. Okay, so yeah, is everyone following so far? Can use Wolfram alpha to calculate eigenvalue in the exam. Well, supposed to be no, but definitely you need to write the steps. Okay, so I think even if you use Wolfram alpha, you need to write the steps. So in the end of the day, you still need to write it out. Yes, sort of. So for the ammonia molecule, right? Ammonia molecule is kind of different. So ammonia molecule is electric dipole, right? So the ammonia molecule is an electric dipole, right? So but also the common thing is we got two states, right? So we were using 1 and 2, or the common thing I guess is both are having two eigenstates, right? But if just now we talk about the silver atom, right? So silver atom or electrons, these are magnetic dipole, and then our two eigenstates are the up and down. Okay, so remember when we ammonia molecule, right? We it's an electric dipole because the electron is distributed in the molecule, so there's gonna be a net positive charge and net electric charge there. But the silver atoms, and this is purely related to the spin. So that is an interesting question. It's like two different phenomena, but the mathematical description is still the same. Okay, usually when this happens in physics, it's worth to investigate a little bit further what's really going on. We do know what's really going on here. It's just both are two eigenstates, but it is a good thing to ask because it's always good to wonder about this. Because when you work on other subjects, right, you see something familiar that reminds you of something, it's usually worth checking out, right? Like you guys will always say, like, right, when you discover something wrong, then Nobel Prize. Usually that is whether it's a Nobel Prize winning work or just other work, but it's noteworthy. That is how interesting papers or projects get written, right? It just starts with that's weird, and then that reminds me of something. So yeah, people have written many papers just because of this, right? So it's always good to have this kind of thinking. Yeah, I mean, exam is something that is also a bit different, right? Okay, how about let me give you a bit of motivation about the exam. At least I guess it's from the lecturer part. Everyone heard of the concept of wormholes, right? You know, in the movie Interstellar, time travel and things like that. And then yes, wormhole is a subject area of research in gravity, right? So that is true, right? So people work on this all the time. But the idea of wormhole, how it gets started, right? It was actually an exam question. Yeah. So so the exam, okay, to be precise, back in Einstein days, there was the Einstein-Rosen wormhole, but it's a non-static solution. So people just consider this and then then forget about it. And then in 1983, there is a relativity course, and then the lecturer set a final exam. That describes the space-time metric, and then after like people thinking about it more, and then at the same time, right? At the same time, I don't know which came first. At the same time, a famous astronomer, Carl Sagan, he was writing a novel called Contact. He wanted to have a realistic solution to describe like space travel, right? So I guess he was like asking this lecturer. This lecturer was Kip Thorne. He also won the Nobel Prize. So Kip Thorne, he was thinking about this, and then at the same time he need to set exam questions. So he set that at the exam question. So I don't know whether he set it first and then told Carl Sagan, or because Carl Sagan asking him this question and then he started to work this out. But basically the exam question, right? And then after that, yeah, this is actually after the exam, a few months later, even after the novel. The novel is some other story, but in research, people realize that this is a valid solution, although it requires some negative energy conditions and things like that. Then people still try to explore, like, how do you construct wormholes and things like that. So even in exams, you can still have some strange discoveries. Okay, so back to finding our eigenstates of the other two. So we found sigma x already, and we found the eigenvalues. Next is sigma y. So sigma y was this, right? And then we want to find the eigenvalues. So sigma y, I want to operate on some unknown state. It will give me some eigenvalue of this. So in order to figure this out, we need to solve this equation, determinant times identity matrix equals to 0, right? So we got lambda minus I minus lambda. Determinant of this equals to 0. So this is lambda square. Minus I will become plus 1, but I'm supposed to subtract this product. So I still got the same eigenvalue equation. So my lambda is still plus 1 or minus 1. Right? So lambda plus 1 on this side, minus 1 on this side. So to find the eigenstates, so this is going to be the plus. So that means what I'm trying to find here is the up eigenstate in the y direction. So I got sigma y up y should be giving me up y. So it's 0 I 0. This is unknown element, so this is AB, right? It should give me back to AB with a positive number, and then I got negative IB IA, right? So this is equals to A and B. So from this, both equation is just telling me that A is just negative IB. So my up vector in the y direction is A, well, negative IB and B, right? So A is equals to this. So I can normalize. So I either choose B is 1 over square root 2. So that just gives me minus I and 1. Okay, so this minus I and 1. And then in the bra-ket form, we recognize that this is 1 over root 2. This is negative I 1 0 and then plus 0 1. So I can express this in terms of my z eigenbasis as minus I up. This is for the eigenstate in the sigma z operator, and this is down in the sigma z operator. So this is the eigenvalue of eigenstate of the sigma y operator, right? So like I said, if even maybe besides the ammonia molecule, you might also find this familiar because we secretly did some similar questions in tutorial 2 already, just that we didn't really know what do these concepts mean, right? Tutorial 1 or tutorial 2, when we are playing around with finding eigenvalues and things like that. For the other operator, it is down y. So sigma x acting on down y gives me a negative down y, right? So 0 minus I 0, AB, and then that should give me negative AB. So negative IB and IA is equals to negative A and negative B. So both parts are basically telling me A is equals to IB. So my down y operator is IB and B. So I can normalize by choosing B is 1 over root 2. So I'm skipping the step of normalizing part because I hope you know what it means, right? The norm must be 1. Right, so for the y part. I guess you know what I mean, right? So I don't need to do the details unless you ask. If you are not sure, then you ask me to show the details. But for now, what we have here is this is hang on, there's an I here, right? So this is I 1 0 plus just 0 1 over here. So now we find the eigenstate of sigma y is I up plus down. And again, I should write z here to be, if you are to be really sure that the differences between the two, I should write here. But when I don't write, it usually means sigma z, because sigma z is our main reference, our main default setting. So that's why I sometimes forget to write the z. But definitely this one we seldom use, right? So we need to say y to remind ourselves that this is the eigenstate of the y sigma y operator rather than the sigma z operator. Okay? Yeah, any questions so far? Okay, so now So now we find the ket bra expression for of sigma y, right? So the spectral decomposition, again, let me remind you of the formula again, because this is quite useful, right? If I can find the eigenstates and the eigenvalues, there's a theorem in linear algebra to show that the operator is actually can be expressed as a sum of this form. So the first one is the eigenvalue of +1 and then up y, and then the other one is the negative eigenvalue, so I got down y. Okay, but how to express this in terms of our standard basis, which is the z basis, right? So what is the up y? So up y is this. So let me put it here. Right, so the up y is 1 over root 2, and then up y is all this stuff. So I got minus I, up z, and then down z, and then see, now that's a complex number, so you have to be careful. Some of you made the mistake last time, so must be careful. What is the bra of this thing? So the bra is dagger, right? You do the conjugate here. If you do the conjugate, means the complex number must flip the sign, so it becomes I up, and then this is down. Okay, so same thing for here. So this is minus 1 over root 2, down y. So down y is I up plus down, and then down bra. So the bra must give a negative sign. Okay, so this is where we have to be careful. Okay, so just simplify this equation. 1 over root 2 becomes a half, and then I multiply out the brackets. So minus I times I gives me up, right? And then minus I up and down. On this side gives me a I down up, and at the back is down. So for the second term, I minus 1, the 2 square root 2's just give me a half, and then I times minus I is up again, plus 1, I, and this is plus I, up down, and then minus down up, minus I, negative I, down up, and then plus down. Okay, so you see how everything works, right? Hopefully by now everyone is familiar in manipulating this. Okay, but right now what we have here is cancellations, and then negative minus negative, so these two is the same, so it will become minus I, up down, and then the other one is plus I, down up. Okay, so this is my sigma y operator in the bra-ket form. Okay, so yeah, so we have found them already, but let me show you the benefit of writing it in this form. We can see how we play around by checking whether how does the eigenvalue equation work, right? So if I take a sigma y, and then let's operate this on the let's do it on the up y operator. Acting on the up y operator, right? So what happens if I do this? So this is going to be minus I up, acting on up down, and then plus I down up, and then the up y eigenstate, which we have found earlier, was, where was it? The up y operator is this, so it's minus I up z plus down z. Okay, so there is a 1 over square root 2, right? And then just multiply out this bracket. So the first term, look at the first term. The first term is, this is the down bra. So if I multiply into this, it will disappear, right? Go to 0. But if I multiply to this, it becomes 1. So I'm left with up times minus I. And then how about the second term? So the second term, if I multiply to this, up minus up, I got a negative I times I. So negative I square is going to become plus 1. And then up bra with the up ket multiply becomes 1. It left behind with the down. Right? Yeah. And then this times this is going to be a 0. So this just back to 1. So what we have found is sigma z times the up y is minus I up plus down. So it's actually the same as this again. So yes, this is really the eigenvalue equation, right? Just that we are expressing it in terms of the up-down basis, the sigma z up-down basis. Okay, so now one of the things that we calculated last time, right, was we have shown that the sigma x, sigma y, they do not commute. So here I want to emphasize this one more time. We have calculated the eigenstates, right? So the eigenstates of sigma z, these are definitely not an eigenstate of the other operator, sigma x, sigma y. Okay, so if it's not an eigenstate, right, if you measure something, then you do not get a different you do not get a definite answer. That means there is a probability associated with it. Okay, so let's take an example, right? So let's take an example. When we're doing the Stern-Gerlach experiment, let's say my silver atom is in the state of up z, right? So remember again, to emphasize that if I don't write, that means I'm talking about the z eigenstate for the poly z operator. Okay, so if this is my beam, right? So if this is my beam, I can measure, right? So if I measure this, then I get the outcomes, right? So the outcomes, I don't want to draw because it's either in the z or y direction. But let's say I'm measuring sigma z. So if I'm measuring the spin in the z direction, for this state, right? So what do I get, right? So I can calculate the probabilities using our usual formula that we have been doing for so long. To get the probability of up, you need to put the up bra here on my state, right? And then modulus square to get what is my probability. So in this case, it's just up. So square, the probability is 1. So therefore, if you do this, then yes, this one is something we have been doing for, should be quite familiar now, right? So if you do this, you get down. So that means if the state is an eigenstate, you get if you measure the corresponding operator, you get your result with 100% probability. But if let's go continue to the next page. Okay, so let's say if I measure sigma x instead for the same state, which is to say that my state is up. So to emphasize, I'm talking about the z direction, right? So what is the probability of getting up, but for the x, because I'm measuring x, right? That means if you measure this operator, the outcomes must be in the basis of this operator. Okay, so I'm talking about this. That what this means is, instead of the up z, I need to do this, right? This x acting on my state over here, right? So what is this? So this is up x, and then acting on this is just up in the z direction. So what is up x? So up x, what we have found was up in the z direction. Forgot already. What was it? The up x direction is, yeah, it's just a plus, right? So it's just a plus, and then I'm acting on my state over here. So this is a bracket, and then I multiply. So this one will get me 0, this will get me 1, and then it's 1 over square root 2 modulus square. So it's just a half. right? And then similarly, if you want to calculate the px down, you need to do this. So it's just 1 over root 2 up down minus the down, right? So yeah, it's the same calculation, but you get here, so what you get here is negative 1 over root 2 square. You also get a half, right? So you got p up x is half, p down x is half. So we get a different probability distribution if you measure in a different basis, even when we are talking about the same state, right? Of course, in some sense, it is expected to be somewhat different because we are measuring the z component of the angular momentum. The z component angular momentum, we know 100% probability is going to be up. But for the x component of the angular momentum of the same state, we are not sure, right? It's half-half. So you can try to do the same for the y angular momentum. Okay, so let's check the time. Block sphere. Block sphere is chapter 7. Although in chapter 7 we do not use the language of the block sphere. So the block sphere is a way to express a two-state system, and it's a very elegant way to express, and it's written down using the density matrix, which we'll introduce in the next chapter. Okay, so we are actually towards the end of this chapter already, chapter 6. So we are going to chapter 7 pretty soon. To close off our chapter 6, right? There's one last example to work out related. Oh, this topic some more. Never mind. There's one more section. I forgot. Anyway, let's work out this example, right? So for this example, we got a spin half particle that is in the state given by this. So this is eigenstates of the sigma z operator. What are the probabilities of getting plus half or minus half if you measure sigma as z, l as x, and then what's the expectation value of the corresponding measurement? So full screen. Okay, so we are doing example 6.2.1, right? My state is 1 over root 6, and then is 1 plus I, and then up, and then 2 down. Okay, so firstly, so if we measuring talking about sigma z, right? So measuring sigma z is basically measuring sz is the same as measuring sigma z, but you times h bar over 2, right? So getting plus h bar over 2 means the state is up. Getting minus h bar over 2 means my state is down. Okay, so let's measure this. The probability of getting up, what is the probability? Well, we just need to do this, right? Up to my state. So this is not an eigenstate of sigma z, it's some linear combination, so no more an eigenstate. But what is it? So it is my up, and then multiply to 1 over root 6, and then my writing must be nice, so to not make it confusing, right? Plus 2 down. Okay, so this is a bracket, so if I multiply this, it becomes 1. If I multiply this, becomes 0. So what I'm left here is 1 over root 6, and then 1 plus I, absolute square. So 1 over root 6, you square, it just becomes 6 outside, and then I'm left with 1 over I, 1 plus I absolute square. Okay, so again, if you're not used to complex number, this is not the square of this, right? When you see an absolute square, the final answer should be a real number. There's no more I anymore. So why is it? Because the reason is because absolute square is not means square, it means times its complex conjugate. So this is just 1 plus I minus I, and then plus 1, right? So the reason why it becomes a real number is because the complex part always cancel each other. So you get 2 over 6, 2 over 6, so you get 1 over 3. Okay, so this is probability up, and then a bit lazy to go through this again, so I'll just say it is 1 over probability up because it's only 2 states, so you got 2/3. Okay, so these are the probabilities of measuring your in the x basis. But if I'm measuring, so this time right now, instead I now measure Sx, right? So Sx is h bar over 2 sigma x. So that means what is the probability of getting plus h bar over 2? So if I'm doing this, it means that my state is the up x state, and then getting minus h bar over 2 means it is the down x state. Okay, so that's why when you say a measurement, right, it is important in quantum mechanics. When you say a measurement, you need to specify which operator you are measuring, right? When you say you measure spin, then you need to say whether it's x or z. The results are very different, as you will see soon. Okay, so if I want to calculate what is the probability of getting up in the x direction, we must do the eigenstate up x here on my state. So this is the important part, right? You don't just use the normal up x. I'm sure that this is a common mistake that it is going to happen, because if you do too fast, you see up, it's so tempting to just quickly multiply the up, but we are talking about up x here, right? So the up x was 1 over root 2 up plus down, right? And then my state here is 1 over root 6 1 plus I up, and then plus 2 down. Is it? Let me see if I remember correctly. Yes. And then this is absolute square. So 1 over root 2 times 1 over root 6, absolute square, it just becomes 1 over 12 outside, am I right? And then, well, what does this become? So up times up, it will give me 1 plus I. This will become 0. This becomes 0. This becomes 2. Absolute square. So what I have here is 3 plus I absolute square. So always remember, absolute square means multiply by its complex conjugate. So what we have here is 9 plus 3i minus 3i plus 1. So this is 10 over 12, or 5 over 6. Okay, so this is my P up in the x measurement, and then the probability of getting down in the down measurement is yeah, again I'm lazy, so it's just 1 over 1 minus this, so it's 1 over 6. See, the two probabilities are so different, right? So you get 1/3, 2/3, but for a different basis you get 5 over 6, 1 over 6. Okay, and then the next part is to calculate the expectation values. Okay, so let's calculate the expectation value of Sx. So Sx for the state, right? And Sx is just h bar over 2 sigma x, right? And what's my state? Well, my precise state is, but let's put the h bar over 2 outside, right? It's just a constant. And then psi is 1 over root 6, right? And then it is the bra, changing this into a bra. So again, changing this into a bra, always remember to do the complex conjugate. So changing this into this, I get 1 minus I now up. And then there's no complex number here, so just keep it like this. And then my sigma x, we have also found the formula for sigma x, right? It's just the Where was it? Yeah, up, down, down, up. Everyone plus. Right, and then my state here is this. So it looks a bit long, but it will suddenly shorten very quickly. So don't worry. Right, 1 plus I, up plus 2 down. Okay, so that is our formula for expectation values. Let's try to get this first, right? So this part is 1 over root 6, right? And then multiply out the brackets. So we got down, multiply to this, it gives me 2 up. And then this one, up times up, multiply, it will give me 1 plus I down. Right, and then the rest are all 0. Okay, so then now I can multiply this now. So 1 over 6, it just becomes 6 times 2, so it's h bar over 12, right? And let's see what we have. Up times up, so I got 2, 1 minus I. And then down times down, so 2, 1 plus I. Okay, so I can actually take out a factor of 2, so it's h bar over 6 now. And then 1 minus I plus 1 plus I. So the I cancel, 1 plus 1 is 2, so the answer is h bar over 3. So this is the expectation values of measuring sigma x. Yeah. Okay, what time are we at now? 53. So yeah, so we have some time, so might as well just finish the last thing, but this is pretty straightforward, right? The sigma z direction. So what we have here is h bar over 2, right? H bar over 2, and then we got 1 minus I, up, and then 2 down, and then the sigma z is just up, up, minus down, down. In fact, let's just keep it as sigma z, because we already know what the relations are. Right, because we are already familiar with the sigma x stuff. So the 1 over root 6, I put it in front. These are eigenstates, so it's just 1 plus I up again, and then the down has a negative eigenvalue, right? And then finally, I forgot the 1 over root 6 here. So outside is h bar over 12, and then just multiply these two. So these two is just 1 square plus 1 square, so it's just 2, right? So it's 2, and then I got 2 and 2, I got minus 4, so it's negative 2 h bar over 12, so it's negative h bar over 6, right? Sigma z. Okay, so yeah, so we have got, so that means if I'm measuring z direction, there seems to be more atoms, negative, right? So there seems to be more atoms in the down component. Is it? Does that make sense? 2. If I square this, 4. 2. Yeah. So absolute square of this is larger than the absolute square of this, right? So there seems to be more atoms in the down state. If I measure in the x direction, there is more direction in the positive x-axis than the negative x spin. Okay, so yeah, so that's it for this revisiting the Stern-Gerlach. What time is it now? So the Stern-Gerlach experiment, right? Yeah, here is obvious, but it is good to check, okay? Because sometimes the state given to you is not normalized, so you need to normalize it by yourself. There was actually a secret trap in the midterm, right? The state given to you was not normalized, so you need to normalize it yourself. To get the correct normalization, the probabilities are probably, it will not affect, but it will affect your statistical results, right, if it's not normalized. So yes, it is good practice to check whether the state is normalized or not. Okay, so that concludes part 2 of the Stern-Gerlach experiment. So we will throughout this course we are like coming and going with the Stern-Gerlach experiment. When we go to chapter 7, we will come back again to the Stern-Gerlach experiment because like Yiming was saying, something about Bloch sphere. We will not say the word Bloch sphere in this course, but we will use the density matrix, and we can express the results of the Stern-Gerlach experiment using the density matrix. So that will be what we are doing. If not on Thursday, then next Monday. So we are going to chapter 7 pretty soon. Okay. So yeah. So I guess now is a good time to take a break. 1, 2, 3, 4. Page 5, page 6. So let's take a 10 minutes break, and when we come back we shall have some presentations, and then I will continue with the Larmor precession, the final topic of chapter 6. So 10 minutes break. Okay, so let me stop the recording. Recording here. Here. Okay, so we are talking about the magnetic dipole moment, and particularly in there's a phenomena called the Larmor precession. Okay, so this is what happens if so just to give an idea of what we are going to study, we are studying what happens to a spin in a magnetic field, right? So it is slightly different from Stern-Gerlach experiment. In the Stern-Gerlach experiment, we are talking about should I write it now? You guys tend to read this later one, right? So I better write it down. So for the Stern-Gerlach experiment, right? So we are shooting a beam of spins through a magnetic field, right? But here in this section, we are considering static non-moving non-moving spins in B, right? The positions of non-moving means what I mean by non-moving is the positions of spins are fixed. Okay, so this one, right, is like the position not fixed. We are shooting it through B. So right, so it's like I have a beam of atoms passing through the magnetic field, and so on and so forth. So this is the slight distinction between these two situations. So this one is ultimately going to be very important for various many different areas of experimental and condensed matter physics, because you have already encountered this in your thermodynamics. For those who are taking who took thermodynamics last time, right? I think you guys talk about paramagnetism, right? You want to calculate what is the magnetization of this. Then so in thermodynamics, you guys are learning everything in the language of partition functions and things like that, because you haven't understand this concept yet. So what is actually happening here is that for a material, right? Material have tiny particles inside. The material consists of many particles, right? And each particle have a spin. So if you put this material in a magnetic field, all the spins will align in a certain directions, right? And this is a quantum behavior. So all the spins will align in a certain direction, and then the material will become magnetized, right? So if we take it out of the magnetic field, some paramagnets, I think if the magnetization will disappear. But for other things like ferromagnets or anti-ferromagnets, it will, even if you remove the magnetic field, it will have its own magnetization. So that's why some materials behave like magnets, because the spins tend to align in the same direction. So other materials, like just normal materials, are not magnets, even though they have spins inside, atoms with spin. And the reason is because the directions are random. So the magnetic fields that they create, they cancel each other out. So and then especially if you are attending those public talks by the main campus, right? So sometimes you see a lot of people mentioning the Ising model, the spins and things like that, and then sometimes you see some Hamiltonian. Hopefully now you understand what they mean. So a lot of this phenomena will be quite important. So let us try to understand this. So as usual, just to help us imagine something, let us begin with a classical picture. So what we are talking about is a spin. We are still exploring what happens to particles with spin. So we go back to a classical picture, and let me draw a spinning charged particle. Well, let's not call it particle, let's call it object, right? Because in classical mechanics, only non-particles like rigid bodies can rotate. So yeah, so maybe this is a bit of a flashback to electromagnetism, right? So let's say I have a charged object, and we are combining different concepts we learned in previous things. So if this charge, let's say it's a uniformly charged, right, classical picture, and if this uniform charge is spinning, right, so I have a particle that is spinning like this. So remember what happens when charges are moving. When the charges are moving, I'm creating a current, right? So if I have a charged sphere that is spinning, then all these particles are moving in circular motion. So that means I've got the current loops. And if I have the current loop, so this is spinning and this is spinning, so therefore the axis of rotation is parallel to the axis S. So this is my spin angular momentum vector. And this is spinning, so this is equivalent to be like a current, right? So if I'm spinning at some omega, then I'm creating a magnetic field around it, right? So it is almost like a dipole. Right? So if this thing is spinning, it creates a magnetic field, right? So this one, it behaves almost like a magnet, right? So this is a classical picture to emphasize. Okay, because when we go to electron is a point particle. It has zero size. Even though it has zero size, but still it has a spin, and then still it has a magnetic field, right? So the spinning creates a magnetic dipole field, right? So it's like a dipole, right? Dipole, remember, the field lines, they look like this. So it turns out that even though this is a classical picture, so yeah, I should stick with classical picture for a moment. This is a magnetic dipole, right? But what I'm talking about is I'm considering spins in an external magnetic field. So it creates its own magnetic field, and if I put this in another external magnetic field, these two will interact, right? The magnet will experience a force acting on this, right? Or a torque. If the positions are fixed and there's a dipole in the external magnetic field, if the position is fixed, remember what's going to happen? It will rotate, right? That it will experience a torque, right? So if you recall the classical picture, a dipole in an external, so I should call this a dipole. So B dipole in an external magnetic field, I'll just call this B because this is going to be our main B, will experience a torque. Right? So then there's going to be a potential energy associated with it, right? So when in the subject of dipoles, we want to calculate the magnetic dipole moment, right? So let me introduce to you the concept. The magnetic dipole moment well, we have seen this before in the electromagnetism, but in this context, for specifically when we're doing electromagnetism, our magnetic dipole moment, we did calculating for a single loop of current with an area A. That is a very simple situation. This is a spinning object, but there are ways to calculate this. The magnetic dipole moment of a spinning charged particle okay, so now let's say it's a particle, because this equation will be valid whether we are in the classical picture or quantum, right? So classical or quantum is given by this formula. Okay, so the magnetic dipole moment is E mu. Okay, if you remember, electromagnetism is current times the area, but for this object in general, it you can show that it's equal to some constant times the angular momentum vector, right, of the spinning object. Because last time is I times A, because we are talking about a current in a wire. This one is something different, but you can show that it's related to this, right? So this gamma here is a constant which is called the gyromagnetic ratio. Gyromagnetic ratio. Okay, so this is another important quantity, and it turns out that it's classical or quantum mechanics, but the value of the constant, it depends on whether it's a classical particle or a quantum particle. Okay, so this part is the derivation of the value is beyond our knowledge at the moment, but I will just write this. I will just tell you, for a classical uniformly spinning sphere, the gyromagnetic ratio is the total charge of the sphere divided by 2m. But for an electron, right, it's not the same value. So it kind of slightly emphasizes that even though electron has a spin, but it's not like the classical picture of a spin, because the gyromagnetic ratio for an electron, right, is the charge over m, right? So there's a missing factor of half. Okay, so the missing factor of half is actually, if I remember correctly, it's kind of like a mystery at the time, because it's something that you kind of, when you do the experiment, this is something that can be measured by experiment, because we know how to measure S, right? And then the magnetic dipole moment is just to do figure out the torque and the energies of the system, so you can get the gamma, and it turns out that the value that you get is off by half, and the reason actually is interestingly come from special relativity. So yeah, so let's just keep it like this for the moment. The reason, because yeah, we can't go into details, is due to special relativity. Okay, and if you are a bit more interested in this topic, the reason is because we can derive the gyromagnetic ratio of this number using quantum field theory, right? So quantum field theory is a theory that is combining special relativity and quantum mechanics. So quantum field theory is usually a graduate level course, so that is why we can't go into the details yet, but for now we just know that gamma is a constant, right? It's a constant that is depending on the situation that we have at hand. But in any case, if you're talking about electron, then it's just a constant that is E over m. In fact, we don't really care what is the specific value of gamma. We'll just keep it as gamma for the moment. Okay? So now let me describe what is the phenomena that we want to study here. Right? So our problem to solve is this. Okay, so we want to study the behavior of a charged particle with a spin. So for example, the electron or atoms, right? So some atoms like the silver atom, they have a spin, and then if you arrange this in a lattice structure, then you get your paramagnetism, ferromagnetism, all those things. Okay, so yeah, so behavior in a uniform magnetic field. Okay, so the positions of each particles are fixed, right? So yeah, so this is the first point, and then the second point is the difference between the Stern-Gerlach. So the Stern-Gerlach is, if you put it in a non-homogeneous magnetic field, it will experience a force, it will accelerate the particle somewhere else, right? So those are particles that are freely traveling through the in free space. But here usually the positions of the particles may be fixed, right? I say may because even if it's a Stern-Gerlach situation or not, the main point we are talking about is we are not calculating its position. Right, so just calculating the behavior of spin. So this thing. Okay, so so for this problem, we won't be deriving the position wave function like we did for the electron around the hydrogen nucleus and things like that. Okay. So yes, and of course, like I said, this phenomena exists whether we are in classical mechanics or in quantum mechanics. But since this is a QM course, we want to describe the quantum physics of this problem. Okay, so what time are we now? Okay, so to describe the quantum mechanics of this problem, we need to solve the Schrödinger equation, right, for every QM problem. And to solve the Schrödinger equation, we need a Hamiltonian. Schrödinger equation. Okay, so I'm kind of taking you through the thinking process of how to understand a system. Okay, so in this example, okay, so let's say you want to understand the phenomena of a particle with spin. So how do you start, right? In the context of quantum mechanics. So if you want to see the quantum behavior, then the theory that you should use, firstly, you decide is to say quantum mechanics rather than Maxwell's or Lorentz force equation, right? Those are classical, but now we are talking about quantum mechanics. So if for quantum mechanics, you need a Schrödinger equation, and for the Schrödinger equation, you need a Hamiltonian. So okay, fine, you decided to say Schrödinger equation. The next problem that you have is, what's the Hamiltonian? Okay, so how do you construct the Hamiltonian of the system? This is also one of the skill that needs to be learned in doing quantum mechanics. So how do you construct the Hamiltonian of the system? The first thing to remember is, well, usually we carry concepts over from classical mechanics. And for the case of the Hamiltonian, well, Hamiltonian, if you remember, is everything that we've been doing so far is Hamiltonian is basically essentially the energy of the system, right? So Hamiltonian is the energy, the measurement operator for energy. Of the system. Okay, so now we understand, okay, energy of a system, and then the next part of your thinking process is, okay, how do we figure out what's the energy of the system? What is the system? The system is a dipole in an external magnetic field, right? So dipole in a magnetic field. So what's the energy of a dipole in magnetic field? So charged particle. So it seems to be a jump, but charged particle with spin is basically a dipole. Right. So that's why I suddenly changed this to dipole. For dipole in magnetic field, well, we did learn from electromagnetism that the energy is, if you know the dipole moment, you take the dot product with my magnetic field. So this formula was, I looked it up, it was equation 5.22 in electromagnetism that we did last time. Okay, so this was the classical formula, but so right now usually what we do in quantum mechanics is, well, since we don't have any other things, we try to this is what we mean by quantizing the formula. So we change this into a quantum operator formula. So I say that this is the potential energy, and then is this equal to my Hamiltonian or not? Yes, because the particles' positions are fixed. It is not moving. There is no kinetic energy of the system. So the total energy of the system is no kinetic energy. There's only potential energy here. So my Hamiltonian is, yes, equals to mu dot B itself. Okay? So that is our process of trying to identify the Hamiltonian. So does this make sense to use this Hamiltonian in the Schrödinger equation? Mu dot B, right? When we're doing electromagnetism, it feels like everything very classical, but our mu here contains the S vector, and S vector can be changed into an operator, right? So this is gamma S dot B, right? So to have a quantum, so if to get the quantum version, right? So to get the, for quantum mechanics, right? S is promoted into an operator, right? So from classical mechanics, it's just a normal vector. But here, for quantum mechanics, we have spent the whole last couple of weeks understanding the spin angular momentum, right? So for quantum mechanics, the spin vector is promoted to the status of an operator, right? In classical, everything here is just a number, okay? And of course, S was h bar over 2, the Pauli matrices. So that means my Hamiltonian is half h bar gamma Pauli matrix times dot product with B. So the Pauli matrix vector, if you recall, it just means sigma x I component, sigma y j component, sigma z k component, where in quantum mechanics these are now operators. Okay, so now I got the Hamiltonian for this phenomena, right? So this is a sigma z dot product with the magnetic field. So magnetic field, for the moment, we still treat this as a classical. That means it's not an operator, just normal vectors. So when you dot product with this, what does this become? This becomes a 2 by 2 matrix, right? And then we solve it in the same way like we did last time in all these ammonia maser kind of things. Okay, so this is a general description for, well, I have a spin particle, right? And if it's an electron, this is negative E over 2, if it's an electron, but for arbitrary particles. And I haven't said what is the magnetic field yet, right? So it's just dot with B, but B could be any formula. So let us consider specifically a uniform magnetic field. So we consider a uniform magnetic field in the Z direction. So if this is the case, right, then my magnetic field is just a constant number times the K direction. Make sense so far? Okay. Wow, 7 more minutes. Suddenly short of time. Okay, so that means my Hamiltonian is just well, what we have here is h bar gamma sigma dot product with the constant number b. So this is a number, right? So this is the number, and then dot product with the k, right? So it's half h bar gamma b0 sigma dot k. What is this? Sigma dot k is just the z component, so it's our sigma z. So therefore our Hamiltonian is just a bunch of constants multiplied by the z Pauli matrix. So this is really a 2 by 2 matrix. H bar gamma b is 1 0 0 minus 1. Okay, so so my Hamiltonian is proportional to sigma z, right? So obviously they commute, then that means they share the same eigenstates as sigma z. So we immediately already solved. We already spent so much time finding the eigenstates here. Then this is just the same eigenstates. So since the Hamiltonian is just a constant times sigma z, then obviously the same eigenstates will happen, right? So the eigenstates of H are the also eigenstates of sigma z, right? In other words, up and down. So up and down are also the same eigenstates of my Hamiltonian over here. So now that we know these are the eigenstates, the eigenvalues are going to be the energy levels. So let's figure out what's the energy. Okay, so let's operate this on my up state, right? So what I have here is, well, it's basically minus half h bar gamma b0 sigma z times the up. So this is just giving me back to up. So I conclude that h operating on up state gives me a negative energy. So half h bar gamma b0 up. So this is my energy eigenvalue. I'm going to call this E. I should be consistent with the textbook. Is E plus, right? So E plus is negative half h bar gamma b0. Okay, so this is my energy eigenstate for the h up. Then if I do for the h down, then my Hamiltonian is half h bar gamma b0 sigma z acting on the down. This gives me negative down gamma. So the result is negative negative, it turns into a plus. Okay, so this is my eigenvalue. So I will call this E minus, but the energy is plus. Okay, it's a bit weird, but the Griffiths textbook do it this way. So once in a while I should try to follow the notation. Although I know I don't follow the notation of all the textbooks, the whole textbooks. Sometimes I use my own, but for this case, at least, yeah. For this case, let's follow this. Okay, so I got two energy levels. This is having a higher energy state than this, right? So in particular, this is a higher energy state. Then up. Okay, so that means if my spin is up, it is a low energy configuration. So if my spin is down, it's having a higher energy configuration. It corresponds to the dipole, right? So if my magnetic field is pointing this way, and then my north pole is it is kind of corresponding to the classical picture again a little bit. If you recall, the magnet will be attracted to the direction of the magnetic field, right? So being attracted, being pulled here is the state of lower energy. If you want to push it to face it the other way around, you need to do work done, because this situation has a higher potential energy. So if you want to face it the wrong way, then you get a higher energy. So this my dipole is facing down, but my external field is facing up. It's the wrong way. So you need to push, you need to input energy to transform into this. So the only difference here, one of the difference here, is that I have two eigenstates. It's either exactly this or exactly this. So the classical picture of slowly moving it doesn't make sense, but what you can do is you can shoot a photon to get an excited energy state. So if you absorb a photon, then it will suddenly transform into this energy level, higher excited state. Okay, so yeah, I guess we don't have time to finish the whole thing today, but I should at least say that now that we have the eigenstates, right? The eigenstates are this. So any arbitrary state can be expressed using this as the basis, right? So can be expressed as a linear combination. Yeah, again, maybe you might feel something familiar to ammonia maser again, right? So that means if if I have an initial state, it is something this plus something this. So if the particle has initial state, what time is it now? Yeah, so I should this is gonna be the last thing. Okay, so I'll just say that it is some combination of down. Remember to normalize, right? Must check normalize this. Then at later time t, we have also shown this as well. Okay, so if I know the eigenstates, then the function the state at any later time t, you just multiply i.e. T over h bar, right? So my up state is having the plus energy, and then b e minus I e minus T over h bar. I forgot this. Okay, so let me write this one more time. And then this. Okay, so this is my wave function at any future time t. So we are kind of solving it very quickly, right? Because we already have our knowledge and catalog of our sigma z operators and their eigenstates. So when we consider a system, then we realize that the Hamiltonian is just a constant times sigma z. We already know the eigenstates, so we already solved the problem immediately here. Okay, so when we continue next week, even though we solved the problem, there is an interesting phenomena that is called Larmor precession. So when we continue on Thursday, we shall derive the Larmor precession formula. So, but besides that, that should be all for today. Okay, and yeah, if there's no other question, then that's all for today, I guess. So let me stop the recording. See you on Thursday.